Yeah, hello everyone and welcome everyone. And it's really nice to see you all. And today I would like to show you what we have built in order to protect our system and our clients from fraud and from fraud attacks. But before we begin, let me briefly introduce myself. So moin, my name is Seb. I'm Director of Technology at Agile. And you might be wondering, what is actually Agile? So we are a fast-growing edtech company. And what we do is we offer unique Oh, I'm really sorry. Yeah. So let's do that over again. I'm really sorry. This was not in the rehearsal. But so again, hi, moin. My name is Seb. I'm Director of Technology at Agile. And you might be wondering, what is Agile? Agile is an edtech company that offers unique tech solutions for apps. We're also based in Hamburg. And so maybe more about us. The company was founded in 2018. We're profitable since 3 years. And we offer our services in more than 190 countries. At Agile, we are currently 65 people that come from 25 different nationalities. And the system as it is now is also a little bigger than it used to be in 2018. Today, we serve around 2 billion requests per day. And now, what is it that we do exactly? So what we're doing is we're connecting advertisers to publishers. But what's an advertiser? An advertiser, you can imagine, is someone like Candy Crush. And they would like to get new users for their app. And what they do is they come to us, and we connect them to the app publisher. And the app publisher has something integrated from us inside their app that enables them to earn ad revenue. And thereby, the publisher shows the ad from Candy Crush. Candy Crush gets new users, and the app publisher earns ad revenue through us. So everybody's happy in the end. Now, speaking of publishers, who of you, I assume many of you are coming also from Germany, who of you in the audience has heard of Payback before? Okay, really nice. So Payback is one of the publishers that work with us. And inside Payback, you would find something that is called the game world. And you as a user would like now to get more points. So you go to the game world. There you are presented with a list of possible games that you could play. So what you do is you install, and then you play. And the more you play the games, the more points you will earn. And then in the end, you can check them out into vouchers, which you can use to buy groceries or to buy clothes. But Payback is not the only publisher. We also have other publishers where you exchange your points, your coins, or whatever, in the end, to real money or to cryptocurrencies. And now we come to the problem, because rewards attract fraudsters. So what are the tricks that they're using? The first thing, maybe you already have heard of it, is country spoofing. And in a nutshell, this looks like this. So let's assume you are a user in Vietnam. Then for you, the playtime experience might look something like this. So for 1 minute of playing, you would get 20 points or 20 coins inside the publisher app. However, if you would have been a user in Germany, you would have gotten 10 times that much. And this is the basic incentive for a fraud user to conduct this country spoofing. And the reason for this difference between the countries are the price differences in the different countries. And now this can cause some problems for our business and for what we do, because the advertiser will in the end also find out about this, that the user did not actually come from Germany, and they will be mad at us because we sold them a user at a much higher price. and they would actually then start to dwindle down the budgets. And then in return, if the budgets are dwindling down, also the ad revenue earnings of the publisher would also go down. So in the end, everybody would be mad if we were to let that pass. So what we have built is a system that protects both the advertisers and the publishers from that kind of ad fraud. So let's take a quick look at how does this system actually look like. And I will only give a brief overview of what it does. So it has multiple systems, and this is not a comprehensive list. But on the one hand, we have a means to detect whether both the device or the app has been manipulated with tools such as Magisk or Frida. On the other hand, we're also able to detect what kind of install source was used to install either the publisher app or the advertiser app. So did the user actually use the Google Play Store or the store? And then we also can take a look at the user behavior data. So is it maybe a ridiculously small amount of time that the user takes to complete a level? Does this actually make sense? However, we also have two other techniques, and this is on the one hand face verification and also an advanced VPN detection. And these are the two topics that I would like to talk to you about today. So let's start and kick it off with a more advanced VPN detection. So let's take a look into the past. How did it look like maybe a couple of years ago? VPN detection would have been relatively easy because most of the time the VPN would be hosted in some kind of data center. And then what you could do is when you see the traffic coming in, you could see, okay, what is the IP of the user? And then you could make a lookup to a Whois service or to some database that you have already acquired. And you could determine, oh, this is actually an IP from a hoster. So this is a VPN, and this is relatively easy. However, the times have changed. And nowadays, what has become prevalent is the existence of residential VPNs, where the VPNs are not consisting of a few data center nodes, but of millions of nodes that are hosted out of some person's home or garage. So you're faced with a problem that you have fraud actors that have access to really a ton of IPs. Everything looks unique and the entire traffic looks normal. You cannot just look them up because the IPs that you have are just basic and normal IPs. And here I have also posted two examples of providers that offer that service. One is an app that offers the users some kind of advantage if they were to share the bandwidth. So there are some users out there that offer their mobile bandwidth, and they are then part of a VPN network. There's another app called which is called Mysterium Dark, which is a peer-to-peer network that offers also a similar service. So this is, in a nutshell, one of the bigger problems that we had been faced with. But there is maybe also a silver lining if you take maybe a closer look at what the VPN is actually doing. So let's take maybe a small look at how the network traffic will look like. So let's imagine you're a client and you're connecting to some backend API. And then you would establish TCP and TLS connection and send network packets over the network. However, let's now imagine you have a VPN in the middle. And the VPN needs to do something to the network packets in order to perform its function. Namely, it needs to know, so at the client side, it needs to know which destination will this packet in the end go to. Because your client will send all of the packets first to the VPN, and the VPN will then route that traffic eventually to the backend. So the packets have to already be manipulated with for the VPN to perform its actual function. And this is what we can use. And here I have an example with Wireshark. So in the first example, you I am interfacing with this backend API just without a VPN. And as you can see, the maximum segment size is now in this example 1440. However, if I interface with the backend API through a VPN, the packets will all be cropped And now I only have a maximum segment size of 1378. And this, in the end, can also be detected eventually in the backend. But backend is maybe too abstract. The backend is actually embedded in some more complex architecture. Usually you have a tech stack that looks something like this. And maybe also as a hint, tomorrow my colleague Fahad will also give you a far more detail about the tech stack. But for now, only the central column will be interesting for us. So when the client interfaces with the backend, it does so not directly, but it will go through something that's called the load balancer. And in our case, it was always the application load balancer. And as the name implies, this application load balancer is operating at the application layer. That also means it is terminating both the TCP and the TLS connection. And all of this valuable information about the packets, the network packets, would be lost at your backend application. So in order to overcome this, okay, I'm sorry, this I just explained. So you would, because this is the application load balancer, you would have no information about the network packets at your application. So what we have built is, or we modified the architecture. Instead of using an application load balancer, we have to use a network load balancer, which is able to transparently transmit all of the packets without modification. And then what we have built is a custom load balancer that is able to read out the packet information and determine, oh, the packets are actually smaller than I would have actually expected, and populate some additional information onto the request. And then inside our application, we can see that. So now we have this information, and our application can now react and block this user. So no more rewards and no more payouts for that user. But you might be wondering, okay, now I'm super smart. I will not be using a VPN. I will use an HTTP proxy because now the HTTP proxy will reestablish TCP and TLS connection, both with the client and with the server. And then this network packet cropping is no longer happening. However, there's also something that we can do against that. And that is because we only allow secure traffic. That means everything has to be TLS, SSL encrypted. And what we can do is we can force that for the hosts that we are using, the certificates are pinned to what we have configured in the beginning. So if you would try to establish a connection from the client to the HTTP, the client should reject this connection because the certificates are pinned. And then this is no longer possible. So in summary, looking at some of the detailed data of the network traffic in the network packets, it's actually also possible to detect surreptitious VPNs that are using residential IPs. But with that, let's now also get to another common problem that we have in our system. And that is the following. So on any kind of problem, on any kind of platform that you might be running your applications, the platform providers made sure that there is no such thing as a very hard to reset device identifier. So both Google and Apple also made sure of that there's not something unique that you can use to find out whether this device had been used before. And this can be also exploited for the fraud that we are dealing with. So what can happen is you see a new device coming to your system. Then the user on this device is installing, collecting rewards, making payouts, and then is resetting all of these device identifiers or any kind of other information. And then you will have another new device. And then the cycle can repeat over and over again. And then this person can collect tons of rewards in order to defraud you. So how do we prevent this? So one of the first methods that we employed, and that was also quite successful, was face verification. How does it work? So you ask the user, once the payout should happen, to verify by making a selfie. So the user would make a selfie with a front-facing camera, and then you would have a unique an image. And once the same user tries to do that again with a new device that was actually just a reset, he comes back, has the same device, and you can then find matches in your database that you have seen this face already before. There's also open source technology that you can use for that. For example, OpenCV supports that, but also cloud providers like AWS offer services that enable you to do face similarity searches. One point to that, if you just look for image similarity or face similarity, you might just be fooled by a photograph that someone holds in front of the camera. But in order to protect against that, you can do something that is called a liveness check. And instead of just making one single image, you're making multiple images that are taken at various distances. So the user would just move the camera a few centimeters back and forth from the face. And because it is a 3D object in front of the lens, the image will behave in a certain way, which you can also model and detect. However, as it turns out, this method is not sufficient, because fraudsters are even capable to fool this. And as it turns out, there are some people somewhere around the world that are able to recruit hundreds or thousands of people to do the face verification for them. So you are now faced with a problem. This device can be reset multiple times, and you have also a lot of faces that you can use. You can imagine someone like an Uber driver that asks one of the passengers to make a selfie after the ride. And so how can we fix this? But yeah, there we did also some research, and I don't know if you also know that the photo itself can also contain information about the camera that took this photo. And here I am not talking about the EXIF data. I'm talking really about the raw pixels themselves. They actually contain information about the camera. And before I go into that, I will first talk a little bit about the details. So how does a camera sensor actually look like? The camera sensor is an array of CMOS sensors. And CMOS sensors are not color sensitive in the visible spectrum. So in front of it, you also have something that is called a color filter array. So in front of a red pixel, there's a filter that filters out everything except red. And then on the blue, everything except blue will be filtered out. And as I have shown here, usually on a camera, you have more green pixels than you have blue or red pixels. So now we come to also a problem of manufacturing, because the manufacturing is usually not perfect. That means some of the pixels will be, due to manufacturing tolerances, be dark pixels. And these can be also unique spots on the sensor that are dark, but more importantly, the response of each pixel can also be different. And response, I will also get to it later, means how much signal do you get out for a certain amount of incident light. And here is so the simple model how this looks like. So on the left-hand side, I have the electrical signal. And this is determined by, on the right-hand side, the response times the incident light intensity. And then there is also always be some kind of noise term. And this is usually governed by readout noise. So you behind the sensor, you have some readout electronics, and this is also usually noisy. So, and you will also always have some noise inside your signal. And what is also a common assumption is that this noise is what is called additive white Gaussian noise. Additive just means I'm adding it to the pure signal. And white means it has no preference for frequency, and Gaussian means it is normally distributed. And this we can use because in order to use this, the fact that the responses are different for each pixel, and this can be this can be a unique pattern for the camera sensor, we have to somehow get rid of this noise term. because it will make the analysis a lot more difficult, or actually impossible. With the noise term, you cannot find any kind of matches. So how can we remove this noise term? And now I'm afraid we will have to use a little math. So what we have to calculate is something that is called a wavelet. So let's imagine this is now for the red color channel, an image. And what you do is you take now this array of pixels, and it's just an array of floating point numbers, or alternatively an array of integers from 0 to 255. And what you do is you can, in the horizontal direction, calculate the difference of adjacent pixels. And you can do that for calculating it for the pixel number 1 and 2, 3 and 4, and so on and so on. And then you will end up with only the odd numbered pixels you keep. These will then be in what is here shown in the upper left corner. This will be called the approximation. And then you have the differences to the adjacent pixels. This is called the detail coefficient. This is shown here in the upper right corner. So, and on top of that, you can calculate this difference not just in horizontal direction, you can do that also in vertical direction and in diagonal direction. And what you will end up is something that I have shown here. And this is called a wavelet. In this description, I have left out a lot of details. A wavelet is a lot more complex, but this is in a nutshell what it is about. Now, what do I want to do? I would like to remove the noise. And as I said, it is additive white Gaussian noise. That means it's normally distributed, and for that there are common filters that you can use to remove it. But for that I need to have some kind of estimate of the variance of the normal distribution. And this is an algorithm that I'm using, and this is not also originally from me. I have also posted here the publication that I have used. So what is it that I will do? For every detail coefficient that I have, so on, let's say, in horizontal direction on the upper right corner, I will take a neighborhood of a very small size, so a 3 by 3 square, for example. And then what I will do is I will calculate the average of the square of this value, and then calculate the average of that value, and then I will assume that the variance will not be smaller than a certain value, sigma 0. And so what I will end up is this value for this particular neighborhood as my estimate for the sigma. And now what I do is I take not just a 3 by 3 neighborhood, I take 5 by 5, 9 by 9, but I cut it off at some point. So I take several neighborhoods, and I take the estimate that is the smallest one for the noise that I have. So what will I have in the end? In the end, I will have for each of the points in the detail, for each detail coefficient, I will have an estimate of what is the sigma of the white Gaussian noise. And then I can apply what is called a Wiener filter in order to obtain the denoised detail coefficient. Then I take the inverse wavelet transform in order to obtain the denoised image, which also visually will also look a lot more smooth. But what is more important is how big is the noise amplitude actually in my pixel. Now, what do I do with this? Here I have posted an example, and also in particular to show you how it works. So I've taken two images with the same camera. And you might be wondering why is this image so green? And earlier I had explained to you, you have more green pixels in your camera than you have red and blue. And when you usually take a picture of yourself, the camera or the app will actually correct this color error, and it will start to mix the pixels in order to obtain the correct, correctly perceived color that a human would perceive. But this is not good for our purposes, because if I start mixing the pixels, the information about them gets lost. This is why I had to change the app, or we had to change the app in order to obtain the really raw image information that I get. And here I don't mean the raw image format, because these images are also in JPEG. I just mean the unmodified pixels. Now, what is it that I do here? So I took these images, I denoised them with the algorithm that I have described before, and then I put them on top of each other, and I calculate the correlation of these matrices. And when I calculate the correlation, I will just get a real number, so some number. And what I have done here on the left-hand side is I do this correlation calculation for different offsets. So I'm moving the images with respect to each other in order to overlap different kind of pixels with each other. And what you can see here, once I have actually found the match where the correct pixels are on top of each other, when I calculate the correlation, this correlation function will peak, and I will have found the perfect match. And this way, even though I don't have any further information, it is possible to find whether two images have been obtained from the same camera. And thereby I can also find out whether this photo or whether this device had been used also before by another one. Now, in the current state, as it is now, this algorithm or this method has a kind of a problem. Or not a problem, it's more like a performance issue that we also are going to tackle. So if you are now faced with, okay, you get from a user an image, and then you have to find out, have I seen this image before? You have to go through the entire collection of images that you have in your database, and this can be time and also CPU intensive. And what we have in mind to fix that is to do something that is called an index lookup. There's something called a BK index. And this BK index, BK tree, would take also as input something like a metric. And the metric in our case can be 1 minus the correlation. And then we can say everything that is within a certain distance of this image, please find me all of the similarities. And this would be a much faster lookup. So what's the conclusion of all of this? The fraud actors that we're dealing with, but also fraud actors that you might be dealing with, are actually very creative at finding loopholes in your system. Using detailed information about the network packets that you receive at your backend can also reveal whether a VPN had been used, even if a residential proxy, a residential VPN had been used before. And also using the photo response non-uniformity, it is possible to match different images in order to find out whether they have been taken from the same camera. And then finally, in order to protect your system against fraud, one has to be vigilant, and you have to be able to play with the system and, so to speak, try to find also some loopholes yourself in order to stop the fraud from actually happening. And this is how we protect app publishers and also advertisers from fraudsters who are then stealing revenue and also destroying publishers' margins. So with that, thank you everyone.